Hello everyone, my name is Suyash Gupta and today I'll be presenting our work ResilientDB Global Scale Resilient Blockchain Fabric. This work I did with Sajjad, Jelle, Mo, and we did at Explorer System Lab, University of California, Davis. So what is this work about? This work about blockchain, and there are several applications of blockchain that we know, like cryptocurrencies like Bitcoin, Ethereum. It is used in waste management, energy trading, healthcare, and other applications. At the core of any blockchain application is a Byzantine fault-tolerant consent protocol that ensures that all the participant replicas agree on the order for the client request. Now, as we're talking about blockchain, and we know at its core is the BFT protocol, and blockchain expects the replicas to be decentralized, and some of these replicas may be geolocated. So we thought of measuring the ping and bandwidth cost. And what we saw is that for locations as far as Belgium and Sydney, the communication cost or the ping cost could be very high and the bandwidth could be very low. And that is our motivation for this work. So we thought of comparing GeoBFT against existing protocols, and we thought as GeoBFT as outperforms all the existing protocols. GeoBFT basically differentiates between local and global communication, and unlike existing protocols, it is not centralized. So how does GeoBFT work? First, GeoBFT is a topology of a protocol. What GeoBFT does is that it takes a set of replicas, it divides them into clusters, and it runs parallel consensus at each cluster. Further, GeoBFT ensures that in each cluster, the combination is low, and between the clusters, the combination is again quite low. Basically, it tries to reduce inter-cluster communication. Here are the steps of GeoBFT. First, each cluster runs PBFT locally, replicates a request, and certifies a client request. Next, each cluster exchanges this request and its certificate with every other cluster. And finally, all the clusters order and execute these requests. Basically, there are three stages in which GeoBFT works. Let's try to go into these stages in detail. Here we'll assume two clusters C1 and C2, and we'll assume each cluster has a set of replicas is n equal to 3f plus 1. Each cluster also has its own client and primary. Every client sends its request to its own primary. And we'll assume for the moment when a primary gets a request, it runs the PBFT protocol locally in its own cluster to create a certificate. At the end of the PBFT protocol, every replica has 2f plus 1 commit messages, and that is what they call as a certificate for the request to be replicated across the cluster. And then these clusters exchange the certificate. If there's a need, they do local sharing. Finally, they order the request, and then they reply to the client. Now let's try to see each of these stages in detail. The first stage is about local replication. Basically, we want each cluster to locally replicate its request and create a certificate. For that, we employ PBFT protocol, the first practical BFT protocol. PBFT assumes in a system of 3f% replicas, at most f replicas could be Byzantine. PBFT requires 3 phases, of which 2 require quadratic communication complexity. In PBFT, safety is always guaranteed, while liveness is guaranteed periods of partial synchrony. PBFT also provides a mechanism for replacing malicious primary, which is called as the view chain protocol. Now let us look at the PBFT protocol. Here we have a system in which n is equal to 4 and f is equal to 1. The client sends a request to the primary. As soon as the primary gets the request, it assigns a sequence number and it sends a pre-prepare message. Every replica, when it receives a pre-prepare message from the primary, what it does is that it verifies the request and agrees to the primary's order of the request by sending a prepare message. Once a replica receives 2f prepare messages, now this replica is aware that there are at least majority of other replicas who also receive the same request. And then it sends a commit message. Once a replica receives 2f plus 1 commit messages, now it has a guarantee that majority of replicas have also prepared this request. And so in GeoBFT, all of these replicas create a certificate that includes the original request and the 2f plus 1 equal to n minus f commit messages. Note that in the original PBFT protocol, replicas would have executed the request and they would have replied to the client. But here, there is no execution replying till now. Next, replicas basically share this certificate with every other cluster. So following this, now next step is to do inter-cluster communication. And to inter-cluster communication, the idea here is that every cluster wants to exchange the certificate with every other cluster. So what do we do in GeoBFT is that we require primary of each cluster sent to F+1 people of other cluster. And how is this optimal? Because there are F bad people in each cluster. So there's a guarantee that F+1 person will be good. And in case if the sender primary, say PC1 himself was malicious, then, and he does not send the message to anyone else, then there's always a guarantee that he will be detected because there are F+1 people. Once replicas of C2 receive messages from C1's primary, now they do a sharing among inside the cluster. At this point in time, every replica has certificates from every other cluster. So now they can go ahead and order the request. For ordering, GeoBFT employs a deterministic policy. Well, what we want to say is that, say we have two clusters CI and CJ, and if I is less than J, the request of cluster CI executed before request of cluster CJ. For example, C1 and C2 requests C1 are executed before C2. You can also employ other complex policies. So we implemented GeoBFT on ResilientDB, and how does that work? Well, ResilientDB associates a multi-threaded deep pipeline architecture with each replica. Let us try to have a look here. Well, we assume first replica is a black box. That means a replica gets all the messages from the network layer, basically gets messages from clients and other replicas. And as ResilientDB provides a multi-threaded deep pipeline architecture, so any incoming message is handled by input threads. These input threads forward those messages to other threads depending on their type. So if there's a client request sent to batching threads for batching, other messages like prepare and commit sent to the worker thread. And if they're certificate, they are sent to certified threads. Some of these messages need to be sent forward to the output threads for sending to other replicas. And if there's a need for execution, we also have an executed thread. So as you can see, there's a lot of parallelism happening here. Now, we're talking about blockchain, so we also need to maintain the chain itself or the ledger. And traditionally, the ith block in the ledger includes the ith execute requests. In GeoBFT, in each round, each replica is executing Z requests. That means each replica needs to create Z blocks in GeoBFT. Basically, each of the requests corresponding to every different cluster is in its own block. And to ensure immutability, what does GeoBFT do is that it also includes client requests and exchange certificates. So we evaluated GeoBFT on ResilientDB, and we did it across 6 different locations with 160,000 clients. And here are the results. As you can see, GeoBFT clearly outperforms existing protocols. In fact, it achieves 1.3 times performance than hard stuff and 3.1 times performance higher than PBFT. Similarly, we employed batching. We want to see, does batching help these other protocols? And we saw that that is not the case. GeoBFT still performs much better than other protocols. So why is this the case? Well, other protocols are sort of centralized because their primary is bandwidth saturated, while GeoBFT allows inter-cluster communication and intra-cluster communication, which helps it optimize the performance. So to conclude, for achieving faster local replication, GeoBFT can also employ other BFT protocols. We can also employ cryptographic techniques such as threshold signatures. If a cluster does not have requests, GeoBFT allows it to send no-op messages. GeoBFT optimizes consensus by reducing global communication cost. Parallel local replication helps GeoBFT achieve higher throughput. Here are the references. Thank you.